Okay, welcome back. So I want to steal 2 minutes of Kostas' time for announcements. So first of all, dinner tonight is going to be at the Natural History Museum. I want to save you the disappointment up front, so I'll tell you now, we're not going to see dinosaurs. We will not have access to the dinosaurs. We'll be eating dinner in a room that has gems and minerals. It's also a very nice room, but we won't be able to wander all around the museum, so it should be fun, but don't be disappointed. To get there, you can exit the building through any exit. Walk down many exits, all of them work for this. What you do is you walk down to Forbes Avenue, you take a left, so you walk in the direction of the hotel, and then you see the museum to your left after like a 5-6 minute walk. We're actually going to enter through the art museum entrance. They're connected. So the art museum is a big brown building that looks relatively modern. The Natural History Museum is adjacent to it, but we'll meet at 5 minutes to 6 near the entrance to the art museum. Okay, so it's the big brown building right before the Natural History Museum. Cool, and it's 5 minutes. We'll finish before that probably, so you can walk leisurely and we'll get done. The second thing I wanted to say is we're still collecting the $4 for nationality rooms. So the box is there at the back of the room. And if you want to come, and obviously all of you want to come, please put $4 in the box. There's plenty of change there, so you can take change as well. Okay, so with that, it's my pleasure to introduce Constantinos Daskalakis. He's an associate professor of computer science at MIT. And Constantinos will talk about, the general theme is complexity. Today he'll talk about complexity in mechanism design, optimal mechanism design, in a way that relates to Rakesh's talk and will also relate to Jason's lectures tomorrow and on Friday. And then tomorrow we'll give another talk about complexity in game theory and things like equilibrium computation. Thanks a lot for coming.
Well, thanks a lot for inviting me, and thanks to you guys for being here. So I'm going to talk about applications of complexity theory and algorithms to economics problems, and I'm going to be referring to, so today I'm going to be referring to Rakesh and Jason for things I don't want to cover. So the plan for the 2 days lecture is today I'm going to talk about revenue optimal auctions and other mechanism design problems. And that's what we call in computer science a positive result, what I'm going to present here. While tomorrow I'm going to talk about the complexity of Nash equilibria, and that's what we call a negative result. And maybe by the end of tomorrow's lecture, it's going to be clear why one is called a positive result and the other one is called a negative result. Despite that, the net effect is positive. Okay, I guess that's the goal of this summer school, realizing the potential from the interaction of these two fields, algorithms and economics. Okay, so so if you want references for what I'm talking about, maybe a good one is this one. I believe the slides are going to be posted, so you'll find the link when they are. So here's the plan. Here's the menu. I'm going to provide a general auction setting. By the way, does anybody have a small battery? If you do, let me know. All right, so I'm going to give a general auction setting. Okay.
I don't have a battery, but I can use mine.
Okay, cool. Thank you. All right. Thanks a lot, Eva. Right, so I'm going to give a general auction setting. I'm going to give background on welfare and revenue optimization. I'm going to present some challenges in the area, and connecting with Rakesh's talk, I'm going to talk about benefits that one can derive by using reduced forms of auctions. And I will conclude with presenting some applications of reduced forms to revenue maximization in multi-item auctions. All right? So here's the auction setting I want to think about. We're going to have an auctioneer who has n items and wants to allocate them to m bidders. And his goal is to optimize revenue or welfare or some other objective. Now, the bidders have values on the items and bundles of items. And the valuation or type of the bidder encodes that information. Okay, so the type TI contains information about how this particular bidder values each item and bundle of items. And it's a complicated thing, right? Because it's encoding a lot of information. And I'm going to make the assumption that these types are drawn from a distribution D. And I'm going to assume that this distribution is a product distribution. I sort of have to assume that they come from distribution because eventually I want to be optimizing revenue. And without any idea about bidders types, it's impossible to solve this problem in a meaningful way. So, but because this is a product distribution, the natural complexity of defining this thing is the sum over all bidders of the cardinality of the type set of the bidder. Because this distribution, it's a product distribution, has to assign some probability on every possible type of every bidder. And I'm going to assume that the bidders are quasi-linear with potentially a public budget. So their utility for getting a bundle and paying a particular price for the bundle is just their value encoded in the type minus the price to pay, unless the price to pay is bigger than the budget, in which case they are very unhappy. Okay. Now, on the auctioneer side, the auctioneer has to decide some allocation of items to bidders. So in this allocation here, this item went to both this guy and that guy, while this guy got both these two items. Okay. And depending on the setting, there's going to be constraints on what is allowed to the auctioneer. And I'm going to use F calligraphic to encode all those constraints that the auctioneer has for the allocation. All right? And these constraints could be matching, some downwards closed system, or something that doesn't satisfy these properties. Let me use this as a cheat sheet here. So D is a distribution over type vectors. Tm, so m is the number of bidders, and I want you to remember F constraints on feasible allocations. All right, so I want to store that piece of notation. So let me give some examples to demystify that if it's complicated. So example number one, selling paintings to people, all right? So in this case, the constraints are that no painting should be given to more than bidders. And hence, my set of constraints is any allocation is good as long as the degree on the item side is at most 1. Second example, where to build a bridge. Okay, in this case, the items are possible locations for building the bridge. Now, the constraints are the following. So if a location, if a bridge is built at a particular location, then everybody can use it. So in particular, if an item is given to a bidder, it's given to every bidder. Okay. So now the set system is all the bidders and any subset of locations. All right. I just want to show how general auction settings fit to the framework I specified in the beginning. Selling paths on a network. In this case, the items are edges of a graph. Every bidder has some source destination pair. And it's a path between these two endpoints. or nothing. And the edges shouldn't be allocated to more than one bidder. So my constraints should encode that information, which I'm not going to write down because I didn't want to do it. Okay. All right. All right. Okay. So what I'm interested in is in general auction settings. Okay? All right. So now, what's happening here? So the auctioneer. So what's the problem we're trying to solve? So the auctioneer has to do the following, right? So the auctioneer has to commit to some auction design that specifies a few things. It specifies what the bidders are allowed to do in the auction, and then what allocation and price rules are going to take place after bidders do whatever they're allowed to do. Then he's going to ask the bidders to play the auction, and he's going to implement the allocation and price rule he promised. On the side of the bidders are going to use as information the auction specification to which the auctioneer committed. They're going to use as information their own type, and they're going to use whatever beliefs they have about the other bidders. And based on that information, they're going to play the auction. And their goal is to optimize their own utility, which I assumed was quasi-linear, so value minus price they pay. On the auctioneer side, I want to optimize revenue or welfare or some other objective. So I don't know how, let me just be formal. So expected welfare is this, right? So now let's parse that. So F is the outcome that the auction decides, the allocation the auction decides. Ti of F is how much bidder I likes that outcome. And I'm summing over bidders and taking expectation over the types of the bidders that are drawn from that distribution D. The randomness in the mechanism, I'm allowing randomization in the mechanism, and also whatever randomness is part of the agent's strategic behavior in this auction. Okay, so is it clear how I parse this expectation?
So the TIs are random variables depending on...
Yeah, exactly. No, so the TIs are the types of the bidders. They are random variables that are drawn from this product distribution. And they define how much TI contains information about how much bidder I likes every possible allocation in the allowed allocations. So TI of F.
Which part of this is random? Why do you take the expectation?
So right, so basically everything is random. So TIs are random. TIs are the types of the bidders.
Okay.
Now, depending on what their types are, they're going to be strategic in how they play the auction. Depending on what they do, the auction is also going to, toss some coins to decide some randomized allocation. So F is the random allocation that the auction will choose, and this is going to be the happiness of people.
Okay.
Right?
It's not the expectation given the bidder types, but it's overall.
Exactly, yeah. Over everything that's random and everything's random. Okay? All right. So what is expected revenue? I'm summing the payments people make to the auctioneer, again, over their types and the randomness in the mechanism and the strategic behavior of it. Okay? Yeah.
So do they pay their value?
Not necessarily. It depends on what the auction is. This is the general framework.
So you allocate the items randomly and then afterwards decide how much each agent should pay for it?
So the auctioneer has committed to some allocation rule and to some price rule.
Okay.
Right? So, he announces that design. Then bidders come to the auction room and they play the auction.
Okay.
And the auctioneer implements what he promised. Right? And they are charged. Right? And the revenue of the auctioneer is the sum of the payments. right? But what these payments are depend on, what bidders showed up, what the types are, how they strategically played the auction, and what, what coin tosses the auctioneer tossed while running the auction, because the auction could be randomized. Make sense?
Yes.
So that's just a general framework. Any auctions, welfare and revenue can be written in this way. I'm not saying anything specific here for any particular auction. The reason I'm setting this up is because I'm going to be optimizing over auctions later on. So I want to be certain about what I'm optimizing. All right? And when I'm talking about optimizing for welfare, I'll be interested in optimizing this thing. When I'm interested in revenue, I'm going to optimizing that thing. But I want to be clear about, what I'm taking expectation over and what the objective function is. Okay? All right, so now, of course, it's absurdly hard to optimize over auctions because there's just too many things that the auctioneer has to decide. And luckily, there is a simplification one can do, which some of you have probably heard about it because I heard you speak about it earlier in a break. But for those who haven't seen it, it's called the direct revelation principle. So that says basically that I don't need to focus in all possible auction designs, okay? Instead, what is true is that any auction has an equivalent one of a simple type from a simple family, okay? So any auction has an equivalent one where the bidders are asked by the auctioneer to truthfully report their types. And it is best for them to truthfully do it. And by equivalent, I mean, no matter what the types are, the two auctions result in the same allocations, the same payments, and the same utilities for everybody. All right, so what the principle says is, give me any complicated auction you want, I can come up with an equivalent one that basically only asks people to report their types to the auctioneer, and the auctioneer takes care of the rest. And the two auctions result in the exact same outcomes, utilities and payments for everybody. Right, so from now on, I'm gonna only be, so what is the upshot of this direct revelation principle? That basically auction design is just an algorithmic problem, okay? So the algorithmic problem is to just find two functions, the allocation and the price function. The allocation function will take as input a type vector, and it's going to output a distribution over feasible allocations. The price function is going to take as input a type vector, and it's going to output a price for each bidder. There's m bidders, as you remember. So that's just an algorithmic problem with the extra constraint that it has to be truthful. Okay, so the claim, the result of the direct revelation principle is that despite the potentially large universe of auctions that one can come up with, it suffices to search over pairs of functions for allocation and pricing subject to truthfulness constraints. Yes?
Is this constructive? Like, if someone gives you a complicated auction, can you construct the simple auction that's...
No. Not necessarily.
Is the price paid regardless of the outcome of the implementation of the random allocation?
Right. So you could have this random if you want. It could be random. So.
I mean, right now it looks like I'm paying.
In advance.
I don't know yet the outcome of the lottery.
Yeah. This is without loss of generality. I can also allow for randomized functions that depend on what allocation is chosen.
Okay.
So if you want some kind of ex post individual rationality, I can do that. but I'm keeping it simple here. Any other questions about the result of the revelation principle? It's very helpful because in principle mechanism design is hard. You have to look at an unknown universe of possible designs. What it says is that I can actually solve an optimization problem to find the optimal auction. And actually, this is going to be an exercise for you. So I ask you to write down a huge LP that looks for a pair of functions subject to truthfulness constraints and optimizing revenue or welfare. Hint, you have to keep a variable for these functions, for these functions. And you have to realize that for both these objectives, revenue or welfare, the objective function of the linear program, as well as the truthfulness constraints, can be written as linear. And I emphasize huge because it's going to be, the complexity is going to be equal to the support of the distribution D. And the downside of such an optimization is that whatever auction is returned by this LP is going to be just a laundry list of what the mechanism is supposed to do in all possible reports of the bidders. So there's going to be there's not going to be necessarily any structure in the output of this huge LP. Question?
So in the previous slide, you had the objective function to be the expectation over all possible types. But now that players are going to give you the types, wouldn't it make more sense to just maximize the sum over the actual types instead of taking expectation, like ex ante as opposed to ex post as opposed to like that?
I don't understand the question.
So the previous slide
Yeah.
had what the mechanism designer is trying to optimize is the sum over all types, but you had the expectation also over the distribution of types, right? But if the types are given to you as part of the mechanism, if you're taking in the types of the agents, why do you have to still try and optimize, still take the expectation over all the types? Why don't you do it on the actual types?
Yes, so
Like if you know the utility functions of the agents, like why don't you just optimize the some of the actual utilities as opposed to taking expectations?
right, so I could do that for welfare. You cannot do that for revenue. So I'm going to come back to this later when I discuss the welfare and revenue objectives. So the short answer is that if you want to optimize welfare, you can do that point-wise over the support of the distribution D. If you want to do revenue optimization, then without the distribution, you are dead. You cannot do this. Yeah.
I think even if you want to maximize welfare on the incentive constraints, they involve different profiles of types, right? So you can
They do, yeah.
maximize point-wise.
Right, but you can do it. You can basically make sure that no deviation. So no matter what the real type vector is, no bidder has incentive to misreport it, and at the same time, the chosen allocation is the one that optimizes welfare point-wise for that profile, and guarantee that simultaneously for all profiles. Also, that's simplification 1 of 2, but it just points out that this is an algorithmic problem, okay? Simplification 2 out of 2, that's a algorithmic simplification. It's without loss of generality, but it's with loss of algorithmic generality. I'm going to be more precise. So in general, an agent needs to specify, so if an agent has to report his type to the auctioneer, he has to specify how he values every subset of the items. And that's a lot of information, so that's exponential in the number of items. There's no way practically he can communicate that information to the auctioneer. Right? So instead, what I want to focus on is on additive combinatorial bidders, which are specified by two things. One is a private vector of values, one value per item. Okay, so the type of the bidder is just a vector of his values for each possible item. And he's also characterized by a public set of constraints on what subset he likes, but it's public, that's important. And his value for a subset of items is the sum of the contents of the subset if the subset is allowed, or negative infinity if the subset is not allowed. Okay, so he's additive as long as you give him something that is not violating his own feasibility constraints. Yeah.
So you said this was a restriction, but it seems maybe I'm not understanding what the general way of doing this would be.
In general, you could imagine, a submodular function over subsets. So a submodular function, so this is the full set, but it's not additive over subsets. So if my value, for a bottle water is X and my value for another lemonade is Y, my value for lemonade and water is not X plus Y. Right? So because, I don't know. So that's the limitation if you look at it this way, but in fact it's not a limitation. Right, so I'm going to give an exercise to that. So the good thing about these bidders is that they can just provide, what they have to communicate to the auctioneer in a direct revelation mechanism is just a vector of n numbers. Right? So algorithmically, it's nice to work with these types of bidders. Note that all unit demand bidders can be thought as additive, because if they have unit demand, then they're just characterized by how much they value each item. And it's an exercise for you to show that if you don't care about complexity, then any setting is really additive with unit demand bidders, and you have to create the right number of the right meta items to convince yourselves. So for the rest of the talk today, I'm gonna assume that bidders are additive, and I'm gonna think of F, the constraints as incorporating constraints of both the auctioneer and the bidders. So last part of preliminaries, and we're done. Let me just be a bit more precise about truthfulness. Yeah.
I have a question.
Yeah.
You start to communicate which the set of constraints, right?
So I said they're public. So I know the guy. Sorry.
You still have to access, right?
Sorry.
You still have to access. You still have to.
So the auctioneer knows the constraints of the bidders.
But it's still exponential. It could be exponentially large.
It could be, yeah, but it's not a matter of communicating it. So the mechanism doesn't need, so the bidder does not have to communicate that to the auctioneer because the auctioneer already knows it.
Yeah.
Okay? Yeah.
Is the allocation of the empty set in any way, is the empty set always in Fi? Or
If you want, yeah, if you want.
because otherwise I might be forced to give an agent negative infinity utility.
Yeah, if if he's I don't know, looking for blood and you don't give it to him, then right? So if you want to, okay.
What's the sense in which focusing on additive combinatorial bidders is not without loss of generality?
It's without loss of generality, but it's with loss of algorithmic generality because the exercise, there's going to be a large number of meta items you have to create to replicate a non-additive setting with a additive setting.
So would it be something like our new items are like subsets of the original? Or?
Yeah, something along these lines, yeah. So in other words, further in the talk, I'm going to give, hopefully, it depends on what I'm making, characterization results. All characterization results of pure economic value do not care about this point. They apply to any types of bidders, but if you want them to be efficient, then this is a class of problems where they are efficient. Okay, are we set with this preliminaries? Okay, so last point, truthfulness. For additive bidders, so truthfulness is easy for additive bidders. It's just linear constraints on the allocation probabilities of the auction. Let me try to explain that. So suppose I specify a mechanism now by the ex post allocation probabilities. So what do I mean by that? So fi of j of a type vector is the probability that item j is allocated to bidder I when the reports are t. Right, so any mechanism induces some marginal allocation probabilities, Fij. And pi of the vector is the expected price that bidder I pays when the reports of the bidders are t. Right, so any mechanism also induces those. So a mechanism is Bayesian incentive compatible if for all bidders and possible types of that bidder, the following inequality is true. It seems bad, but it's not. Okay. So I'm taking expectation over the types of all the other bidders on both sides. And now inside here, I claim that this is the value of the bidder for the outcome of the mechanism under reports V. And here's where I'm using additivity. So if a bidder has type VI, then his expected value for getting phi j's is exactly this inner product. Is it clear? So I'm summing over all items, the probability that the bidder gets that item times his value for that item. Right? And I'm subtracting the expected price that he's going to pay. Right? And this is his utility if he reports truthfully his value, VI, to the auctioneer. And here's how his utility would change if he misreported and said VI prime instead of VI. Then he's going to be paying a different price. And he's going to be making different probabilities for each item. And this inner product is going to be modified. Right? So what you want for a Bayesian incentive compatibility is that he prefers to say, if his true type is VI, he prefers to say VI than to say VI prime over what types he expects the other bidders to be. Yeah.
So if I has any information on the other bidders, they could break this, is that right?
Right, so if I knows, right, so if your mechanism just satisfies this inequality, it may not be truthful for bidders who have various kinds of information about the other bidder. Yeah.
You say expected price. What is the expectation with respect to this?
Again, just
The randomness of the mechanism.
yeah. And the mechanism is incentive compatible if the same is true but without expectations here. Right? Yeah.
The distribution of types, are they independent?
It's a product, yeah.
You said before it's a product.
Mm-hmm. So right, so otherwise I would have to be conditioning on my own type in this equation. All right, so these are the preliminaries. Hopefully, this is standard mechanism design setup just for completeness, okay? All right, so as I mentioned, there's two main objectives in mechanism design, optimizing welfare and optimizing revenue, and let's see what we know about those objectives. So the welfare optimization problem is a well understood one, and there is a well-known result, the VCG auction. So the theorem is a reduction, Okay, so this is the viewpoint I want to take. I want to take the following viewpoint, that the VCG auction provides a reduction from a problem to another problem. Okay, so what the theorem says is that mechanisms designed for optimizing welfare is not harder than just designing an algorithm for welfare optimization. Okay? So the VCG auction is a computationally tractable reduction from mechanism to algorithm design in the following way. So here's how VCG works. So the bidders are asked to report their types to the auctioneer. The auctioneer chooses in the set of feasible allocations the one that optimizes welfare, okay, the sum of happiness of people for that allocation. So that is done by calling a welfare optimizing algorithm. Then the bidders are charged appropriately so that they are incentivized to report their true types to the auctioneer. And the way the truthfulness inducing payments are computed is again by calling a welfare optimizing algorithm. So what the VCG auction provides is a way to, given an algorithm that does not care about incentives but can optimize welfare, right? So given such an algorithm, the VCG result provides a way to construct a mechanism that does care about objectives, incentives, that also optimizes welfare. Okay, so the VCG auction is a reduction, really. This is the viewpoint I want to take. So the corollary of that is that the only bottleneck to tractable welfare optimizing mechanisms is whether or not there is a computationally efficient algorithm for the underlying welfare optimization problem. Right? So if the underlying welfare optimization problem is tractable, then so is designing a mechanism for the same set of constraints F. Right? I believe Eva might have talked about VCG in her talk, so I'm not going to give the details of how this happened. Yeah.
So in your first or second slide, you gave your bidders budget constraints.
Yeah.
So here you're dropping that.
The VCG cannot deal with budget constraints. The technology I'm going to show later can do it. So, yeah. So here I'm talking about the VCG auction, which does. And okay, so coming back to your question, so the VCG auction actually does something much stronger. It does not require a distribution over types, and the welfare is optimized pointwise. Okay? All right. So, so here's the corollary I mentioned earlier. The question is, suppose that the underlying optimization problem is not tractable. Okay, so then what do we do? Yeah.
What is DST mean?
It's dominant strategy truthful. It's something stronger than incentive compatibility. So it basically says, no matter what the other guys are, I don't even need to know their types. I'm better off, reporting my type. Right? So coming back to this question, so suppose that if the underlying welfare optimization problem is algorithmically tractable, then so is mechanism design. But how about if it's not algorithmically tractable? So then what do we do? Okay. So suppose that I can only approximate the underlying algorithmic problem to within a factor of alpha in the objective function in polynomial time. Can I, is there a mechanism that optimizes welfare and achieves the same approximation factor? So this is not answered by the VCG mechanism. The VCG mechanism is not robust to approximation algorithms. So what should we do here? So this was a question that received a lot of attention from the computer science in the computer science literature, and there's two answers to the question. One is a negative answer, and one is a positive answer. So the negative answer, which follows from a long line of research with positive and negative results, concludes that in general, without having a prior over types for bidders, it's not possible to, given an alpha approximation for the welfare problem, design an alpha approximation for welfare optimization in an auction. All right? So without a prior over types, it's not in general possible. On the other hand, and this is what I want to focus more, because I'm focusing on Bayesian settings in this lecture, is in a Bayesian setting where I do have a distribution D, it's actually, there is a general reduction that converts an alpha approximation algorithm to an alpha approximation mechanism for welfare. Okay? So these are, the benefits of having a prior and looking at the Bayesian problem. Okay? Eva?
You must make some assumption about your prior, or else even a full information version has a prior. Like you must say something like independent, identical, something.
No. So, a full information setting, it's just one, there's only one thing in the support. This is what you mean? So then I can just implement whatever is optimal. So it's not, you see what I'm saying? So I'm not ranging, so if I have a point mass on a particular type profile, I just implement whatever is optimal. That's the optimal auction. In order for computational complexity to come in, you have to have a set of possibilities. You don't know which one. You have an algorithm that takes as input one, right?
But you're assuming the underlying problem is infactorable, right?
Yeah. You can only approximate to within a factor of alpha.
Okay.
The question is it in general true that if I can approximate a problem to within a factor of alpha, I can also have a mechanism that achieves the same factor? Yeah.
Do we assume that the bidders have unbounded computation, or they can figure out their optimal bid even no matter what your mechanism is?
So it's going to be direct revelation truthful auction, so they don't have to do anything. They just submit their types to the auctioneer. These are the result of this reduction is a direct revelation truthful mechanism, big mechanism. Yeah.
So how hard is it for the bidders to actually verify that it's compatible?
They have to read the proof of this paper and understand it.
No, but for a given auction, how hard is it to verify that that's the dominant strategy?
So they either explicitly check all possible scenarios, which are a lot, or they read the proof of the if you're using this auction, they read the paper and convince themselves.
I think your question is how they can verify that you actually use this mechanism?
No, because I'm committing, I'm announcing the design of the auction.
You're announcing it, but they may want to verify ex post whether you've actually used this mechanism.
All right, so if you read the paper, what happens there? So here's the answer. So the interface of the bidders to the algorithm is a VCG auction. So what happens in this reduction is the bidders face, when they enter the auction house, they face a VCG auction. And it's, if they understand that they have to play late truthfully in a VCG auction, they understand that they have to play this truthfully as well. So it's easy. So they basically come in and participate in a VCG auction with some, replicas of themselves. Okay. So if they understand that they have to play truthfully in a VCG auction, then they understand they have to play this truthfully. Okay. So it's not something like super crazy that they have to verify. Yeah.
Does the quality of the approximation depend at all on what the choice of the distribution is?
Yes. So that's why I'm putting this in quotes, and I don't exactly say theorem. So there is so this alpha becomes an alpha minus epsilon, and epsilon has to do with how much time you want to spend in this reduction. Okay, so what I want to conclude with is that for welfare, we understand the problem very well. So if the underlying algorithmic welfare optimization problem is tractable, we can get a mechanism. If it is only approximal, we can still get a mechanism with the same approximation factor. All right? So let's consider revenue now. How about revenue optimization? So here the understanding is not as good. So Myerson celebrated result that Rakesh mentioned and proved in his lecture is that if you're only interested in selling, if you're interested in selling a single item, so if you're in a single item setting, or maybe you have a single item, many copies of the item, then again, mechanism designed to optimize revenue reduces to welfare optimization. Right, so Myerson again provides a reduction from a mechanism design problem to an algorithmic problem. So here's a cartoon version of how Myerson's auction works. So bidders are asked to report their types to the auctioneer. Now there's only one item, so their types are single dimensional. V1 through Vm. Vi is the value of bidder I for the item. The auctioneer takes these bids and converts them to what is called virtual bids. And then it allocates the item to the bidder who virtually likes it most. Okay, so this is a call to a welfare optimization algorithm, and it charges the bidders in a way that their initial reports are to the truthful ones, and again, the payments can be computed by calls to a welfare optimization algorithm. Okay, so in other words, Myerson, as the Vickrey-Clark-Groves mechanism, provides a reduction from a mechanism design problem to a algorithmic welfare optimization problem. So again, if the underlying welfare optimization problem is tractable, then so is the revenue optimal auction. As long as you're not in a multi-item setting. You either have one item or you have many copies of the same item. You can't have heterogeneous items. So the questions that are unanswered by Myerson's work is how go beyond single item settings, and whether you can accommodate approximation. So so it could be that the underlying welfare optimization problem is only approximable tractably. Can you design a approximately optimal revenue auction? Right, so what do we know beyond Myerson? There is a large body of work in economics studying this question. You can look at this survey if you want to learn more, but the progress is sporadic. And recently, the past 5 years or so, algorithmic tools have enabled progress in this field. And the progress comes in two ways: either constant factor approximations to the problem of revenue optimization, or providing exact solutions, but in very limited settings. Okay. And the techniques that appear there are ad hoc. Okay. So in the slides that I'm going to post, I'm going to give an overview of what results are known in the algorithmic literature for welfare optimization. But let me summarize it here by saying that the settings that can be solved with algorithmic techniques are either for unit demand bidders or additive bidders with capacity. No interesting combinatorial constraints on what allocations are allowed. So and again, so the techniques are ad hoc. So the main challenges going forward are: can one optimize revenue in general multi-item setting in a way that provides a unified solution to the problem? Then beyond revenue and welfare, can one optimize other objectives? All right, so for other objectives, even in single item settings, single dimensional settings, we don't have a lot of progress. So example, minimize max span in a scheduling auction. When your objective is not a linear one. Finally, robustness of your solutions to approximation and complexity. Okay? So there are some challenges in this area. And so I'm going to focus mostly on revenue optimization in this talk. All right. So the goal is to provide you with a framework that will allow you to optimize revenue and other objectives. And I want to provide a unified framework for dealing with such mechanism design problems. And it's gonna, the framework is gonna build on reduced forms of auctions that Rakesh talked about in his tutorial. So let me repeat what a reduced form of a mechanism is. It comprises the interim allocation probabilities of the mechanism. So the reduced form provides, for every bidder I, it provides a function that maps his types to probabilities. Let's look into those probabilities. So for a particular type of bidder I, pi ij is the probability that item j goes to bidder I if he reports ti to the auctioneer, and in expectation over everything else that's random. What else is random? So the types of the other bidders are random, and also the coin tosses inside the mechanism are random. Okay, so the interim rule is how much bidder I, what's the probability bidder I with which bidder I expects to get item j if he reports ti to the auctioneer. All right? Is that a recognizable quantity from Rakesh's talk?
Are these independent across objects? So for different topics, the probability that
No, they're not. I mean, so these are marginals of a complicated allocation rule. You have no control of, how these probabilities, you have no, obvious understanding of how these marginal allocation probabilities come about. It could be some complicated allocation rule that marginalized over bidders and items results in these probabilities.
It could be non-anonymous.
Yeah, so I'm considering non-anonymous reduced forms. Okay, where the algorithmic problem is harder than anonymous ones. Okay? So the upshot of looking at auctions from this perspective is that the complexity is the right one. Okay, so if you remember, this is the complexity of specifying the distribution D, and describing a reduced form is linear in that complexity. And compare it to the bad complexity of ex post allocation probabilities, which replace the sum with the product. What is bad about the reduced form is that it's hard to check if a given reduced form is actually feasible. Okay, why is that? Well, so the question is, can the per bidder marginal allocation probabilities be reconciled in a mechanism that respects also the potentially crazy combinatorial constraints of the setting? How do I know that a collection of marginal allocation probabilities comes from something that respects the feasibility constraints of the mechanism? Okay, that's the algorithmic question. The algorithmic question is, given such functions, can you reconcile them? Can you come up with a mechanism that has these probabilities as its marginals? All right, so let's look at an example of a trivial setting, so a single item setting, except non-anonymous one. Okay, so we have two bidders. Bidder 1 is type A or type B uniformly random. Bidder 2 is C or D uniformly at random. And there's one item, and suppose that I'm giving the following reduced form. Written here. So for instance, this says that, if bidder 1's type is A, he's guaranteed to get the item, no matter what else happens in the auction. So this says that if bidder's 2 type is C, then he expects to get the item with probability 1/2 in expectation of what happens in the mechanism and in expectation over the type of the other bidder, and so on and so forth. So this is the meaning of the reduced form. The question is this reduced form feasible? Can I come up with a mechanism that projects to these probabilities? So what is your guess? No? Okay, let's that's correct. So let's try to, it's easy to figure out that it's not feasible. Let's see. So suppose that the reports of the agents are A and C, right? Then I claim that I'm forced to give the item to bidder 1. The reason is that I have promised bidder 1 that whenever he says A, he gets the item, for sure. So when the reports are A and C, A has to get the item. The same is true if the reports are A and D, because A is promised to always get the item if he says A. Once I have committed to these 2 decisions, type A is satiated. Why? Because he knows that if he shows up and says A, he gets the item, right? Now, C is critical because I've already consumed some of C, right? So in particular, if the reports on B and C, I have to give the item to C, right? Because when type bidder 2 reports C, then with probability 1/2, the other guy is going to say A, and he's guaranteed to get the item in that case. With probability 1/2, the other bidder is going to say B. In that event, I can afford to give the item to bidder C, and if I make that commitment, now C is happy. Right? What is the trouble? The only decision I haven't made, these are forced decisions. The only decision I have not made is what happens when the reports are B and D. In order to satisfy these marginal allocation probabilities, if you just do the algebra, you'll see that in this scenario, B needs to get the item probability 40% and D the probability 8%, which obviously I cannot satisfy because I have 1 item. So this particular form is infeasible. And it was easy to check because my first 3 decisions were forced, and it only remained to verify that in what was not forced, I couldn't actually do it. Okay? The question is what happens for more general reduced forms, even single item ones. So Rakesh presented Border's theorem. So linear constraints on a reduced form for it to be feasible. Let me try to review it, but in this non-anonymous setting. Okay, where I have a different reduced form for different bidders. And different bidders have different typesets and different distributions on these typesets, but they're independent. Okay, let me try to derive first a necessary condition for a reduced form to be feasible. Okay, step by step. So let's see. So what is this quantity? So this quantity is the probability that bidder I's type is Ti and I gets the item. So that's the probability his type is Ti, and this is the probability he gets the item conditioning on reporting Ti to the mechanism. So far, so good? So now let me fix a subset of the type set of that bidder. So what is the sum over all Ti's in that subset of this quantity? It's the probability that bidder I's type is in this set that I've fixed, and I gets the item. Right? So now let me fix a subset for each bidder and sum up this quantity over I. So that's the probability that there exists a bidder I whose type is in the corresponding set Si, and he gets the item. So that's this quantity. Now let us look at this quantity. So this quantity is the probability that there exists a bidder I whose type is in the set Si. So which of these two quantities should be larger? This is the probability that there exists a bidder I whose type is in the corresponding fixed set Si. This is the probability that there exists an I whose type is in Si and I gets the item. So which one is larger? Right. So this has to be true. If the reduced form is feasible, consistent with the mechanism, this has to be true no matter what sets I fixed. All right. Recall that in the anonymous setting, this summation had an n in front just because it was a symmetric problem, and the corresponding side had a power instead of a product. So this is the generalization of the same inequality. All right. So that's a necessary condition for the reduced form to be feasible. So what Border proved for the anonymous setting, and then what Border and these people proved for the non-anonymous setting, is that this condition is also a sufficient condition for feasibility. All right. So this is a necessary and sufficient condition. And it's a linear condition on the PIs. Okay, so you give me the PIs, I have to check all these linear inequalities to tell if the reduced form is feasible or not. Okay, again, this is for single item settings and product distributions over bidders. Right? So the exercise for you is to argue that this necessary sufficient condition follows for the max flow min cut theorem. And hint, you're going to have a flow network that has a source S, a sink T, and in between it's going to have types of people and vectors of types of people. And you're going to set up the edges and the capacities on that network so that you obtain that it's going to be the reduced form is feasible if and only if these conditions are true. Okay, these conditions are going to be corresponding to cuts in the network. All right, so the issue is that there is too many inequalities, and there is so many inequalities, and this is practically useless. Okay. So it has been improved to something like this, which is still useless. Why? Because if I were shooting for something like that, I could replicate it with a trivial LP. Okay, so let's look at the LP. So how can I tell if a given reduced form for a single item is feasible? So I can write down an LP as follows. I can introduce as variables the ex post allocation probabilities, right? So for every vector t, I'm going to have a variable saying, if that was the vector, what's the probability that the item went to bidder I? Now, this ex post allocation probability better be a feasible one. So it has to be, these have to be probabilities. I should also not over allocate the single item that I have. Right? So this constraint says that the expected number of bidders that receive an item under any type profile is at most 1. And I have to make sure that the given reduced form is actually the result of the ex post allocation probabilities that I'm computing in this LP. And there is so many variables and inequalities in this linear program. So basically, I can, instead of doing borders inequalities, I can just solve this LP and tell if a given reduced form is a feasible one. If I find ex post allocation probabilities that are consistent with my reduced form, then my reduced form is feasible. If I fail, if this LP is infeasible, then the reduced form has to be infeasible. All right? So the obvious questions are, can the border conditions be reduced to something more manageable? And the other question is, given a feasible single item reduced form, is there a succinct description of a mechanism that projects to that reduced form? Right? The trouble with answering question 2, so maybe question 1 is tractable, but the trouble with answering question 2 is that there's no guarantee that there's going to be a succinct mechanism that marginalizes to have a particular reduced form. It could be that the only mechanism that is consistent with the given reduced form has description complexity of this type, right? In the sense that, to describe a mechanism, in principle, you have to specify the ex post allocation rule of the mechanism, and the ex post allocation rule of the mechanism has to specify what it does in every vector of types. So it's a priori not clear if one should hope for a positive answer to that question. Right? So I'm going to try to answer these questions. So answer to 1, can we reduce the border conditions to a manageable size? So recall the border conditions. So here they are, right? For all sets S1 through Sm. So here's the theorem. So suppose that the type sets of the bidders are disjoint. So that if you want, that's without loss of generality. Assume that every type carries the name of the bidder it belongs to on it. Okay. And normalize the PIs as follows. For a type A belonging to bidder I, define pi hat of that type to be the interim probability that was given to us, scaled by this probability. What's that probability? That probability is the probability that a random type drawn from the distribution of that particular bidder is going to receive a marginal probability smaller than the probability of that particular type, A. All right? So it's not really important how I define this function, except that it exists. So here's the rest of the theorem. So now, order the types in this set in the union. So because I assume these are disjoint, the union has exactly sum of TI's things in it, types in it. So order the types in the union of the type sets in decreasing order of this function pi hat. The claim is that the given reduced form is feasible if and only if the border conditions hold for a prefix of the ordering defined by p hat. So in other words, I only have to check sum over Ti conditions to tell the feasibility of a reduced form. So let me go back to the example I showed earlier. So here it is. So this was infeasible, if you remember. So let me see the theorem in action. So the pi hats corresponding to this setting are these, ordered in decreasing order. So if you want to verify that I did the calculations correctly, here's how I calculated this 0.2. This 0.2 was the underlying probability times the probability that a random type of that bidder had marginal allocation probability smaller than 0.4. So this is what it came out to be. So the theorem says that, if the reduced form is infeasible, then one of these sets is going to witness the infeasibility. So either A by itself, or A and C, or ACD, or ACDB. And indeed, you can see that this set actually witnesses the infeasibility of a reduced form. I'll post the slide so you can check did the calculations correctly. But if you just if you want to keep the final point, so we can get rid of almost all of the border conditions and only keep so many, right? And if you pass these conditions, then you are feasible. Right? So answer to 2, I'm not going to give details, but so that's independent work of these two groups. So checking the feasibility as well as implementing a single item reduced form can be done in time polynomial in the natural description complexity of the problem. And that description complexity is better in that work. It's quadratic in this thing. Okay? So the answer to both these questions is positive. And as I said before, it's surprising. It's not necessarily obvious that this answer should be positive, because maybe the only possible allocation rules consistent with something, a given reduced form, are very complicated. But they turn out not to be complicated. They can be computed in time polynomial in this. All right? So now, which brings me to, so far I consider single item reduced forms. And the question is, can I check feasibility, can I do the same, can I develop such a technology for general reduced forms, so for multi-item reduced forms? So suppose I'm in a setting where I have many items, I have arbitrary feasibility constraints on what is possible, and I'm also given a reduced form. So for every agent, I'm given a function that maps his type to a collection of probabilities specifying the marginal allocation probability of every item. The question is, can I check whether this is a feasible reduced form, one that satisfies these constraints? So and the answer to this question is has the same spirit as it's a reduction. Okay, so the result is, if I have an algorithm that solves the welfare optimization problem for f, that suffices for me to be able to, in polynomial time, decide whether something is feasible. So in other words, the only algorithmic problem that's relevant for revenue, for welfare optimization, for single item revenue optimization, and for deciding whether a reduced form is feasible is really the ability to solve the underlying welfare optimization algorithmic problem. This is what the theorem says. Some proof ideas very fast. So the proof goes by taking a geometric viewpoint on the reduced form. So the reduced form is a collection of functions which I can embed in large enough dimension so that I'm in Euclidean space. Okay. I can just concatenate all the probabilities to a huge vector. So I'm in this space. So the first thing and then suppose that this is the set of all possible reduced forms. So reduced forms that respect the constraints f, and they're subject to the underlying distribution of types. Okay. So the first claim is that this set is a polytope, convex polytope. So it's not some crazy shape in Euclidean space. It has to be a polytope. And the reason is very simple. Basically, a feasible form is implemented by a mechanism. A mechanism is maybe randomized. So if it's randomized, it's a distribution over deterministic mechanisms. Right? These are the deterministic mechanisms, and M is a distribution over those. Each of those has a reduced form, and you can verify that the reduced form of M, which is P by assumption, is a convex combination of these reduced forms, of the reduced forms of the underlying deterministic mechanisms. So every feasible reduced form is a convex combination of reduced forms of deterministic mechanisms. So just an easy argument. right? So that's easy. If you know what randomization means in algorithms, if you can convince yourselves that a randomized algorithm is a distribution over deterministic algorithms, this follows through immediately. Okay, so that's not the important point. So here's the important point. This is surprising and important point, that the vertices of this polytope have a very nice unexpected property. So the claim is that the vertices are reduced forms of very simple mechanisms. So the vertices of the polytope are reduced forms of allocation rules that maximize virtual welfare. Right, so before showing why this happens, let me first say that so reduced forms are projections of allocation rules. So in particular, in principle, there could be many mechanisms mapping to a particular reduced form. So a reduced form could be the result, the marginalized. There could be many mechanisms that marginalize give that particular reduced form. So what this says is that among all these reduced forms among all these mechanisms that may map to a corner, there is a very simple one. And let's try to uncover the structure of this simple mechanism that maps to a corner. So here's the set of feasible reduced forms. Here's a corner. So the corner must be the optimal point in this polytope in a particular dimension W. All right? So pi is the unique optimum of the inner product of pi prime and W, where pi prime is in the set. Right? So it's a vertex of the polytope. So there has to be a W such that in this direction of W, pi is the best point in the polytope. Right? So now let's write down this thing. Let's expand it. So pi prime times W is the sum over all bidders and the sum over all items and the sum over all types of that bidder of Wij for A times pi ij for A, which I can expand in this way if I make this definition. So I make this definition, phi j of A, so this is a bidder, this is an item, this is a type of that bidder, is the ratio between the Wij and the probability that the type of that bidder is A. So let me call this phi ij. Let me interpret it. It's just a definition that depends on Wij for whatever direction happened to optimize that corner and the underlying distribution. So let me interpret that as the virtual value that bidder I derives if his type is A and I give him item J. Let me just assign this interpretation to this quantity. So if I assign this interpretation to this quantity, then this expression here is the expected virtual welfare achieved by the allocation rule pi prime if I use these virtual functions to map types to virtual types. And because of this derivation, it follows that pi is the virtual welfare optimizing reduced form when the virtual functions are the FIs. All right, so in other words, a simple derivation and definition give rise to interesting structure here. Okay, so the outcome of this calculation is that the VCG allocation rule with the appropriate virtual functions is exactly mapping to that corner. And that gives rise to a characterization result. So if you didn't follow the previous derivation, just take home only this slide. So let me define a virtual VCG allocation rule by providing a collection of functions. Function fi maps the type space of bidder I to Rn. Now, the virtual VCG allocation rule with these virtual functions works as follows. It takes as input a type vector. It transforms the type vector into a virtual type vector. And then it optimizes virtual welfare. So it optimizes welfare, but using these virtual types rather than the true types. This is what I define to be a virtual VCG allocation rule. It maps types to virtual types using the functions, then optimizes welfare by calling an algorithm that optimizes welfare for that setting. So the characterization result says that the reduced form of any mechanism can be implemented as a distribution over VCG allocation rules. The upshot of that is that a virtual VCG allocation rule is only specified by providing these functions, and these functions have the good complexity, not the bad complexity. These are full-blown allocation rules. There is a succinct description of them, but these are ex-post allocation rules. But their description complexity is only in terms of these functions, and their complexity is small rather than bad. Okay? And the claim here is that any reduced form is a convex combination of reduced forms of such things. Oops, I didn't want to do that. Right, so coming back to here, the vertices of the polytope are reduced forms of virtual welfare maximizing allocation rules. And the third claim is that if I have not only the thing is convex polytope and the corners have a nice structure, but also if I have an algorithm for maximizing welfare for these constraints, I can turn it into a separation oracle for this polytope. So these are the three tools that give a framework for. So with these three tools, I can decide on whether a reduced form is feasible, because I can obtain a separation oracle for this polytope. And B, I can decompose any point in here as a convex combination of corners, and the corners have a very good form. So now, why are all these relevant? Let's look at where I intend to use these things. Okay. So let's look at revenue optimization in multi-item settings, a problem that's not well understood, using this reduced form technology. Yeah? So here's an LP that optimizes revenue. It's fully specified, except it contains a line I'm going to get to in a little bit. So what are the variables for this LP? So pi I of v for all bidders and types vi is the price that bidder I expects to pay if he declares vi to the mechanism. Pi ij of vi is the marginal allocation probability. That's the reduced form of the mechanism. Okay? So these two constraints make sure that the mechanism I'm about to compute is going to be Bayesian incentive compatible and individually rational. And the objective of the LP is the expected revenue, because this is the probability that bidder's I type is VI, and that's the price he's going to pay, conditioning on being of type VI, and I'm summing over all bidders and all possible types for those bidders. So this LP tries to find a reduced form that optimizes revenue and is big, Bayesian incentive compatible, individually rational. The only thing that it's not, if I omit this constraint, we don't know if it's feasible. There's no line here in the constraints makes sure that the reduced form is feasible. And for that, I'm going to use the separation oracle for reduced forms that are constructed that I talked about in the previous slide. So for setting up such an LP, I really need a way to tell if the reduced form I'm optimizing over is feasible or not. And if you haven't heard of separation oracles, take it as granted that if I have an LP that has constraints, linear constraints, right, and then it has a separation oracle, it has an algorithm that tells if something is feasible, then you can actually solve it efficiently. Okay? Right, so such an LP can be solved in the right running time, given that the separation oracle is efficient. And the upshot is that whatever the optimal solution is, the optimal solution is going to have a nice structure. It's going to be a distribution over virtual VCG allocation rules. So what comes out of setting up this LP and having a framework for reduced forms in place is the following theorem. It's a generic reduction from the mechanism design problem for revenue optimization to the algorithm design problem for welfare optimization. And the result is the following. So suppose that the bidder types are independent, and suppose that we are given access to an algorithm that optimizes welfare for a particular set of constraints on what allocations are feasible. On the other hand, the number of bidders, the number of items, and the set system F is unrestricted for the purposes of this theorem. The claim is that the revenue optimal auction for this generic auction setting can be computed in polynomial time with polynomially many queries to this algorithm for optimizing welfare that is provided to us. And the optimal auction has a very nice form, succinct form. It's not a laundry list of what the mechanism is going to do in all possible vectors reported by the bidders. It has a very simple structure. The bidders are asked to report their types to the auctioneer. The reported types are transformed to virtual types using bidder-specific functions. And then the algorithm that's given to us is invoked to optimize virtual welfare. And prices are charged so that the whole scheme is truthful, is Bayesian incentive compatible. So this is exactly what's happening in Myerson's case. The difference between this and Myerson is the following, that in Myerson's theorem, the virtual functions were deterministic, and Myerson provided a closed form for these virtual functions. In our case, the virtual functions are randomized, and they are computed during the execution of the linear program that I showed in the previous slide. Right? So I point out that they have to be randomized. So it's known that in multi-item settings, there's no deterministic auction that optimizes revenue. So they have to be randomized. There has to be randomization somewhere in the mechanism. And in this scheme, it shows up in the functions. The function mapping, the functions mapping types to virtual types are randomized. So that's an application of reduced forms and the technology that I developed in the previous slides. So the summary is the following. So mechanism design for welfare optimization is well understood in all kinds of settings. The VCG auction provides a reduction to the corresponding algorithmic problem, and there has been a robust reduction that is robust to approximation. The same is not true for revenue and other objectives, and for other objectives even in single item settings. So Myerson's auction optimized revenue in single item settings, but multi-item settings are not well understood, and other objectives are not understood at all. And the main point from this lecture is that reduced forms provide a general framework for tractably reducing mechanism design for whatever objective you have, as long as it fits the framework, to the algorithmic problem of optimizing welfare for the same set of feasibility constraints. And as a application of that, I showed a generalization of Myerson's theorem to all multidimensional settings. And the sort of like, so the theorem was that the revenue optimal auction is a virtual welfare maximizer which can be computed efficiently. And the techniques are geometry and the ellipsoid algorithm. And standard properties of the ellipsoid algorithm, nothing too fancy about it. Okay? And something I haven't put in the slide. So this reduction is also robust to approximation. So it's not sensitive to approximation. So if you have an alpha approximation algorithm for welfare, you can get an alpha approximation algorithm for revenue as well. So that's it. Thanks for your attention. And if there is any other question, I'll be happy to take them.